Materials are the building blocks of our world. They shape our technologies and define what we can build. For centuries, we relied on nature to provide these materials. We mined metals, cut wood, and sculpted stone. But what if we could go beyond the limitations of natural materials? What if we could engineer materials with properties not found in nature? This is the exciting promise of metamaterials. Metamaterials are artificial materials engineered to have properties not found in nature. These properties arise not from their chemical composition, but from their carefully designed structures. Imagine building a material atom by atom, tailoring its structure to achieve specific electromagnetic responses. This precise control over structure allows metamaterials to interact with light and other electromagnetic waves in extraordinary ways, bending, absorbing, or even amplifying them in ways never before possible. The ability to manipulate electromagnetic waves in this manner opens up a world of possibilities, from super-resolution imaging to cloaking devices and beyond. By carefully designing the building blocks of these metamaterials, we can access a whole new realm of material properties and unlock unprecedented technological advancements. Within the diverse field of metamaterials, single-negative SNG metamaterials stand out as a particularly intriguing group. Unlike conventional materials, which always exhibit positive permittivity and permeability, SNG metamaterials are characterized by having either a negative permittivity or negative permeability. Permittivity, often denoted as epsilon, describes a material's ability to store electrical energy, while permeability, denoted as U, represents its ability to support magnetic fields. SNG metamaterials are further categorized into two main types: epsilon-negative ENG and mu-negative MNG materials. ENG materials exhibit negative permittivity while maintaining positive permeability. This means they interact with the electric component of electromagnetic waves in unconventional ways. Conversely, MNG materials possess negative permeability but positive permittivity, leading to unique interactions with the magnetic component of electromagnetic waves. These unusual properties arise from the distinct structures of ENG and MNG materials, which are meticulously designed to resonate at specific frequencies. This resonance is key to achieving negative permittivity or permeability, leading to the unique electromagnetic behavior observed in these materials. Let's delve deeper into the mechanisms behind ENG and MNG materials. Imagine a grid of thin metallic wires spaced closely together. This simple structure forms the basis for many ENG metamaterials. When an electromagnetic wave, such as light or microwaves, encounters this wire grid, the free electrons in the metal wires start oscillating in response to the wave's electric field. At a specific frequency, known as the plasma frequency, these oscillations become resonant. This resonance is crucial for achieving negative permittivity. At frequencies below the plasma frequency, the oscillating electrons effectively screen the electric field within the material, leading to a positive permittivity, similar to conventional materials. However, at frequencies above the plasma frequency, the electron's inertia prevents them from keeping up with the rapidly oscillating electric field. This results in a phase lag between the electron oscillations and the electric field, leading to a negative permittivity. This negative permittivity has profound implications for the behavior of ENG materials. For instance, it can lead to the bending of light in the opposite direction than expected, a phenomenon known as negative refraction. This unusual bending of light has sparked immense interest in developing new optical devices, such as superlenses that can overcome the diffraction limit and image objects with nanoscale resolution. Mu-near zero, or MNG, involves unlocking negative permeability with split-ring resonators. While achieving negative permittivity with metal wire grids is relatively straightforward, attaining negative permeability is more challenging. This is where split-ring resonators, or SRRs, come into play. SRRs are tiny metallic rings with a small gap, resembling a key ring with a break in the ring. These structures are meticulously designed to resonate with the magnetic component of electromagnetic waves, typically in the microwave regime. When an electromagnetic wave with a magnetic field component perpendicular to the plane of the SRR passes through it, the changing magnetic field induces a circulating current within the ring. At a specific frequency, this induced current resonates with the SRR's structure, leading to a strong enhancement of the magnetic field within the ring. This resonance is key to achieving negative permeability. At frequencies below the resonance frequency, the SRR behaves like a typical magnetic material, exhibiting positive permeability. However, at frequencies above the resonance, the induced current lags behind the changing magnetic field. This phase lag results in a negative permeability, indicating that the SRR opposes the external magnetic field. This unique property of negative permeability opens up exciting possibilities for controlling magnetic fields at the microscale. It forms the foundation for developing novel magnetic devices, such as magnetic cloaking devices that can guide magnetic fields around an object, rendering it invisible to magnetic sensors. The power of combining ENG and MNG materials leads to anomalous tunneling and beyond. While both ENG and MNG materials exhibit remarkable properties individually, combining them unlocks even more astonishing phenomena. By carefully stacking layers of ENG and MNG materials, researchers have created metamaterials that can manipulate electromagnetic waves in unprecedented ways. One such phenomenon is anomalous tunneling. Imagine a barrier that normally blocks the passage of light or other electromagnetic waves. Now, imagine placing a thin layer of ENG material followed by a thin layer of MNG material on one side of the barrier. Astonishingly, this combination can allow a significant portion of the waves to tunnel through the barrier, even though neither material alone could achieve this. This counterintuitive phenomenon arises from the interplay between the negative permittivity of the ENG material and the negative permeability of the MNG material. The ENG material essentially pulls the waves towards the barrier, while the MNG material helps to push them through, leading to an enhanced transmission through the barrier. Beyond anomalous tunneling, the combination of ENG and MNG materials has also led to other extraordinary discoveries, such as electromagnetic cloaking and perfect absorbers. These advancements highlight the immense potential of SNG metamaterials in revolutionizing various technological fields. In conclusion, the future of SNG metamaterials is incredibly promising. Single negative metamaterials represent a paradigm shift in material science, offering unprecedented control over electromagnetic waves. From bending light in unusual ways to enabling anomalous tunneling, these artificial materials hold immense promise for a plethora of applications. Imagine a world with super-resolution imaging, allowing us to visualize objects at the nanoscale with unprecedented clarity. Envision cloaking devices that can render objects invisible to electromagnetic waves, opening up new possibilities in stealth technology and secure communications. These are just a glimpse of the potential that SNG metamaterials hold. As research in this field progresses, we can anticipate even more groundbreaking discoveries and applications. The journey into the world of SNG metamaterials has just begun, and the future holds exciting possibilities for harnessing their extraordinary properties to shape a better tomorrow.